Hello everyone. So today we will see a very important concept about prime number and uh, divisibility, and we will try to prove this claim. It's a very simple mathematical logic, and we'll try to prove this claim and see in upcoming videos where this concept can be used. It's actually very important. So first of all, try to read this claim, and then we will go about the proof. So the claim is that given a number n, there can be at max one prime divisor of n such that it is greater than square root of n. So let's try to understand it by breaking it down. So if you are given a number n, it can have many prime divisors, right? Like let's say if you have 90, 90 has prime divisors like 2, 3 and 5, right? So it says that there can be at max one prime divisor of n such that it is greater than square root of n. So I'm saying that if you have given me prime divisor p, I can very well say that if it is greater than the square root of number n, then I'm sure that this will be the only number which will uh, divide, which will be greater than square root of n, and it will divide n. No other prime number greater than square root of 1 will divide it. Okay, let's try to prove this. So we know that any number can be represented, any integer in fact can be represented as a product of its prime raised to power certain powers. So we can say that n equals p1 to the power alpha 1, p2 to the power alpha 2, p3 to the power alpha 3, and so on, pm to the power alpha m. Like you can see an example, like we can say that 90 can be represented as 2 times 1, 2 is a prime number of course, 2 times 1 times 3 times 3 raised to the power 2 times 5 raised to the power 1, right? So let us now see. So can we say that uh, okay wait can we say we will try to prove this by contradiction. Okay, so let's try to, can we say that wait a second, p1 times p2, let's say we have a number, this number n itself, and we can say that p1 times p2 times p3 pm, this is less than or equal to p1 to the power alpha 1 times p to the power alpha 2 pm to the power alpha m, right? This equality will hold when alpha 1 alpha 2 all of them are equal to 1, right? We can say this. So now let's assume that, and we can also say let's say that we have two prime numbers. We are claiming that we will have two prime numbers p5 and p7, and both of them are greater than square root of n, let's say. So what we are, okay wait a second, so I'm saying that pm is greater than equal to square root of n, and p7 is also greater than equal to square root of n. Okay, now can we say that uh, p5 times p7 is less than p1 times p2 times p5 times p7 times pm, and this is lesser than lesser than p1 to the power alpha 1, p2 to the power alpha 2, pm to the power alpha m. We can say this, right? So now if you see, if both p5, wait, now if you see that Now we claim that both p5 is greater than or equal to square root of n, and p7 is also square root greater than. Now if we say that this is greater than square root of n and this is also greater than square root of n, then the product will definitely be greater than n, right? So if this part is greater than n, then this part will definitely be greater than n, right? And then this part will definitely be greater than n, which is wrong, right? Because this is actually equal to n. So our claim that we can have two such numbers is wrong, right? In fact, if you take three such numbers, it will again be wrong, right? But if you take at max, you can have just one number, right? So we'll see some examples. Let's say there is a number 34. We can write it like 2 times 17, right? And what will be the square root of 34? So square root of 34 will be around greater than 6, and so okay, not greater than 6, like lesser than 6 and greater than, let's say 5.5 something. So we can say that there is one prime number 17 which is greater than the square root of 34. Okay, one thing you should keep in mind is that this does not, this we are specifically talking about the prime divisors and not just the divisors. So a number, let's say a number 36 can have multiple divisors, like it can have even 3-4 divisors which are greater than its square root, but that does not mean that it will also have prime divisors which are greater than square root. Let's see. So we can write 36 as 2 times, okay, let's write down the divisors of 36, which will be 2, 3, 4, 6, 9, 12 and 36, right? They are all divisors of 36. So if you see, the square root of 36 is 6, and we have like 1, 2, 3, 4, we have like 4 divisors of which are greater than square root of n. But here in this case we are only talking about the prime numbers. So if you see, greater than 6, there are in fact 0 prime numbers which are dividing 36, which actually is correct, because our claim was that there can be at max one prime divisor of n. Okay, so in this video we just covered like what this claim is. Even though this claim might sound a little obscure and you might feel like where are we even going to use it, we'll see some examples. In fact, we use it in prime factorization. I just wanted to give you a heads up. So yeah, let's see in the next video. Bye bye.